Hi everyone and welcome. In this video, we're going to take a look at a pretty fun limit question. It's a little bit on the trickier side. And we are going to attempt to solve the limit as x approaches infinity of 2x minus 3 divided by 2x plus 5, all of this raised to the 2x plus 1 exponent. I encourage you to take a moment to pause the video and think about how you might go about solving this. This one is a little bit tricky, so don't worry, I will walk you through how to solve it. But in case you do come up with a different solution, feel free to let me know down in the comments below. I'll love to see different approaches, maybe even more efficient than mine. Okay, so let's get started. The first thing I noticed is that the inside is a rational function, and the degree of the numerator and the degree of the denominator are both 1. They're both equal. So that means in the long term, as x approaches infinity, this expression should approach the ratio of the leading coefficients 2/2, which is equal to 1. And the way you can formally show that is you want to divide by the highest power of x in the denominator, and that's usually how we approach these types of problems. But in this case, I want to instead do long division. I want to do polynomial long division to rewrite this term so that it's more clear why this approaches 1. So let's review how we do polynomial long division in case you haven't seen that recently. So we begin by taking the first term of the dividend and dividing it by the first term of the divisor. Well, 2x divided by 2x just gives me 1. That goes right over here. Then you want to take this and multiply by the entire divisor. That gives you this expression. And now you subtract. What you get is minus 8. So this is your remainder. This is your quotient, right? This is your dividend. This is your divisor. And so now we can write the division statement in quotient form as saying the dividend divided by this divisor gives me this answer or quotient plus some remainder that I still need to divide. So in this case, the remainder is minus 8, which I still need to divide by my divisor. And so now what we're going to do is we're going to replace this with this new form. And now I hope you can see that it's a little bit more clear that as x approaches infinity, this will just go to 0. This is just 1. So yeah, this inside just approaches 1. And this is 1 to the infinity. And 1 to the infinity is an indeterminate power. And so let's take a look at how we take care of that. Okay, so we're going to rewrite this function so that it's no longer of the indeterminate form 1 to the infinity. And the way to do that is you want to remember that e and natural log, they're inverses, they're inverse functions. So we're going to take this and we'll write this as e to the natural log of that thing, right? Because these cancel out and you get exactly back here. And so now I'm going to use one of the properties of the logarithm to bring this exponent down. And so we get this expression. Okay, so instead of computing this limit, we're going to compute this limit, which is just a different representation of the same function. And by the continuity of e to the x, we can push this limit sign through to the exponent. And so we can say this. Okay, and so now what we have to do is figure out this limit. And this limit we actually can do because this is a indeterminate product. You can see that this approaches infinity, and we know that this inside approaches 1, and natural log of 1 is 0. So this is an indeterminate form of 0 times infinity. And so I'm going to show the work on how to compute this limit in just a moment. But it turns out the answer is going to be minus 8. This is just equal to minus 8. And so therefore, the original limit evaluates to e to the power of minus 8, or 1 over e raised to the power 8. Okay, great. So now let's take a look at how to compute this indeterminate product limit. Okay, so I have rewritten the indeterminate product here. And as we discussed, this first term approaches infinity. The inside approaches 1. Natural log of 1 is 0. So we do have an indeterminate product of the form infinity times 0. Now, L'Hopital's rule does not apply to these indeterminate forms. But the idea is you want to convert this into 0 over 0 or plus minus infinity over infinity. And the way you want to do that is actually bring one of these functions down. So if you have a function f times g, you can do f over 1 over g. Or you can also keep g on the top and then do 1 over f. And so this will actually convert it into 0 over 0 or infinity over infinity. And so in this case, I would like to bring the linear term down. And so I'm going to divide by 1 over 2x plus 1, which is equivalent to the original function. And now, as you can see, this is of the form 0 divided by 0, right? 0 divided by 0. So L'Hopital rule does apply in this case. And so we're going to differentiate the top and bottom separately. the derivative of the natural logarithm is 1 over the input. The input in this case is this mess. And then by the chain rule, you have to multiply by the derivative of that inside. And so the derivative of 1 is just 0. And then to differentiate this function over here, you can just think of it as 2 to the x plus 5 raised to the negative 1 power. And so by the power rule, you can write this as bring the exponent down, 2x plus 5 raised to the minus 2, multiplied by the derivative of the inside, which is just 2. And so that's why the minus sign over here canceled out with this minus sign. And then the 8 times 2 gave me the 16. And I moved this back down to get this. Great. And so you can apply a similar idea on the bottom to differentiate this. Think of it as 2 to the x plus 1 to the negative 1, and then apply power rule, and you'll get this. Don't forget the chain rule. That's how I got the 2 inside. Okay, so the next thing we're going to do is we're actually going to work with this expression here and try to simplify it, rewrite it as a nicer fraction. Right now, this is a little bit too complicated. So let's go on the side and let's work with this fraction and see what we can do. Okay, so here is the same expression we just had. What we're going to do is we're going to get common denominators here so that we can make this into one big fraction. So that means I have to write this as 2x plus 5 over 2x plus 5, and then that becomes one big fraction there. We'll leave this term the exact same. And then if you're dividing by a fraction, well, then you can multiply by the reciprocal or the flip. And so that's what I've done over here. I've multiplied by the flip. Okay, and now what we can do is clean this up over here. We will just get 2x minus 3. And then this can go back on the top. And so you get 2x plus 5 on the top and the 2x minus 3 on the bottom. And everything else has stayed the same. And now what you can see is that some cancellations happen. For instance, we have 2x plus 5. We have 2 of these factors, so we can cancel one of them over here. And we can reduce the fraction over here as well. And so in the end, we get this rational expression, which is definitely much easier to work with. And so now let's go back and substitute this where we came from. Okay, so just a few moments ago, we were at this step, and then we went on the side and we reduced this to the following rational function. And now we're taking a limit at infinity of a rational function. Well, how do we do that? Usually you want to divide by the highest power of x that shows up in the denominator. Well, in this case, the denominator is a quadratic. It's a second degree polynomial. And so for that reason, I am going to divide both the top, the numerator, and the denominator by this x squared term. And so what's going to happen is that we're going to get this x squared, but then you can just write that as divided by x, all of this squared, and then you can just cancel over here with x and over here with x, and you get this form. So you get 2 plus 1 over x squared. Similarly, this one's a little bit much simpler. We can just take the x squared, divide this one by x, divide this one by x. And so that means you can divide each term in here by x's. And the x's over here cancel. And this just gives you 3 over x. The x's over here cancels. And this gives you 5 over x. And you get this expression. Now when we take the limit, we see that this term approaches 0. These terms just approach 0. And so really we have minus 8, 2 plus 0 squared. In the bottom, we have 2 minus 0 times 2 plus 0. So 2 squared and 2 squared on the bottom, those just cancel, and you just get minus 8. And so therefore, the value of this indeterminate product that I was mentioning before is indeed minus 8. And so now we can go back and substitute that into the original problem, and we'll see that the answer is e to the minus 8. And so as you can see over here, that's what we did over here. We replaced this with minus 8 and get our final answer. And so there we go. That brings us to the end of this video in which we solved this somewhat complicated looking limit. It required quite a different techniques. We had to work with indeterminate powers. We had to work with indeterminate products. We also had to take infinite limits of rational functions. So many different techniques built into this one limit. So very, very nice. The answer was simply e to the minus 8 or 1 over e to the 8. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.